new for us. Everyone cross your fingers.
Welcome, everyone.
Okay. Hi, welcome to tonight's talk,
Oh,
which is
we're not quite ready yet. Let's get the live stream going first.
sorry.
Give me
Okay.
just a
It
moment.
takes it takes a minute, and we'll probably give folks like another minute or two
Mhm.
to join.
All right.
For sure. For sure.
Your folks are punctual, though. I appreciate all the people who are on here
Yeah.
already.
Thank you so much.
I love your backdrop, Chris.
Thank you. It calms me when I have work meetings.
Uh,
Like it's very relaxing, and
mhm.
All right. We are live on
Thank you.
YouTube.
Hello, world.
Laura, let me know whenever you want to get started.
We are live. Liz, are you ready? Liz?
I yes,
All right.
I am ready. Sure.
Okay, fantastic. Uh, I'm just going to ask that everyone who's not speaking go on and mute yourself. And we'll start with Donna. Give me a welcome.
Okay. Hi, folks. Welcome to tonight's talk, which is presented by Hampton's Observatory with co-host Auroras. I'm Donna McCormick, Executive Director of Hampton's Observatory. And for those of you who don't know about us, we were established in 2005 for the purpose of fostering interest in science in general and astronomy in particular. And to that end, we have a small observatory in East Hampton, New York, which is currently under repair. But when we're finished, we hope to make it remotely accessible to students, researchers, teachers, and the general public so they can just explore the universe and do the research. We also hold star parties and a number of different educational programs like the one you're attending tonight. All of our public programs are free of charge, so everybody can enjoy and learn about the universe around them. And if you'd like to learn more about our organization, you can reach us at hamptonsobservatory.org. You could also use that to join our email list for event notices and news about what's going on. This lecture is being recorded and it will be available in a few days, a week or so, on Hampton Observatory's YouTube channel, as well as on the YouTube channel of excuse me, Aurorasaurus. Feel free to post any questions you have in the chat. They will be answered at the end of the lecture. And I want to thank you all for attending. I'd also like to thank Dr. MacDonald for taking the time to share her expertise and to thank Aurorasaurus for collaborating with us on this program. And a special shout out to Laura Brandt Edson, who is the project manager of Aurorasaurus and who will be taking it from here to introduce Dr. MacDonald. Thanks, folks.
Thank you so much, everybody. I just want to add to the list of thanks our wonderful volunteer, Tanya, who will be monitoring the YouTube chat. So folks watching on YouTube, please feel free to place your questions in the YouTube chat, and we will also be relaying those to Dr. MacDonald at the end of the presentation for the Q&A. So now I'd like to introduce Dr. Elizabeth MacDonald, who works for NASA's Goddard Space Flight Center remotely from her hometown of Walla Walla, Washington. She leads this global citizen science project we call Aurorasaurus, which uses citizen science and social media to predict the northern and southern lights. In 2018, Dr. MacDonald announced the discovery of a new aurora called STEVE, which stands for Strong Thermal Emission Velocity Enhancement. Say that 5 times fast. She has been studying the glitter of the northern lights for 25 years, and it never ceases to amaze her. She's also led teams that build instruments to measure charged particles in the space environment for NASA and DOE satellite and rocket missions. Outside of work, she enjoys skiing and hiking in the Pacific Northwest, and we're very excited that she was just named one of this year's Explorers Club 50. It's a wonderful award. So passing it over now to Dr. Elizabeth MacDonald.
Thank you so much, Laura. I'm excited to be here virtually with all of you tonight. Just checking that you are seeing the slides correctly and that you can hear me all right.
Looking good.
Great. Thank you so much. All right. Well, after that great introduction, I will get started telling the group more about understanding Aurora and also about ways that you can actually participate in Aurora research with Aurorasaurus. And that is our project. I am from NASA's Goddard Space Flight Center. Our project is also supported by the National Science Foundation and run with the New Mexico Consortium. And I also am affiliated with Whitman College here in Walla Walla, Washington. But my sister used to live in the Hamptons, so I've been there once. That's a story for another time. But I did want to tell you a little bit about my background and influences. I like to start my public talks with this. And, people say, how did you become a physicist? And I never would have imagined becoming a space physicist. I grew up mostly in Walla Walla, but prior to that, my family had moved from New York State when I was a kid. And my dad loved the natural world, and my mom taught math and really enjoys a lot of math. So those were some of my early influences. But still, I had no idea what real research was and interest in that. But I was very fortunate to get a scholarship to attend the University of Washington. And that included undergraduate research. So I was able to learn what physicists did in their jobs. And I actually was very fortunate to be matched with someone, my mentor Ruth here, who studied the beautiful northern lights and built instruments that study how they work, the electricity and magnetism that happens in our upper atmosphere and causes some of the really beautiful, complex mysteries of the northern lights. So that seemed like an interesting application of physics, and I was able to keep going and pursue that in graduate school as well. And I am I would say, an amateur aurora hunter, certainly an amateur photographer. But I spent a lot of my early career at Los Alamos National Lab in New Mexico, and I worked on instruments that measure the space environment from further out than the atmosphere, from like geosynchronous orbit. And also we contributed to instruments that measure the Earth's radiation belts and satellites for NASA with that. So that's been an exciting part of the journey, kind of the lab work that I used to do. And one day I got the idea for what would become Aurorasaurus. That was over 10 years ago now. And since then, I have kind of shifted what I do to where this is the majority of what I do. And it is also very rewarding and interesting, as much so as even launching rockets and flying things in space. So both things are really interesting. And now I know you know a little bit about me, and I would love to learn a little bit more about you all, and whether you have ever seen Aurora before. I'm hoping that you are like many of my audiences in the last year, and that you have actually seen Aurora during some of the really large storms over the last year. And that's why you're here, to learn more. Oh, great. Lots of hands up. That's a good way to do it. I can actually see the hands. And then also, yeah, you've seen Aurora before, ever. The last year has been a great time to see it. And then raise your hands if you have done citizen science or participatory science before. And there are a couple people with their hands up here. Maybe like me, you could be a birder or a forager, something like that. And I think, let's see, has anyone here taken part in citizen science with auroras? I think we have a few super fans here who have contributed to our project. So thank you for all of those folks. And hope to see more people contributing with your photos by the end of the talk. So, and lastly, two more questions. Raise your hand if you love nature. Seeing lots of hands go up. Excellent. Yeah. And if you think helping with scientific research sounds fun. So you definitely have what it takes to be a citizen scientist, to make discoveries, and that's what we're going to be talking about today. So really excited. Thank you for the participation. What I'm going to be talking about, we're going to back up a little bit to define the field that I'm in, which NASA calls heliophysics, and what that is. We have been having a really big year with, I'll tell you more about it, not just the auroras, and tell you a little bit about ways that people can participate in science, and then talk about the open questions and how more about auroras kind of throughout all of that. But the first definition that I wanted to share is that heliophysics is just the study of the sun and its effects throughout the solar system. So that is a really large system. The sun has a magnetic field that extends way, way out beyond all the planets. And we live in the extended atmosphere of the sun, and we have our own magnetic field and atmosphere, and how those things interact. And the physics of that is heliophysics. So aurora, there are the northern lights, the aurora borealis, and the southern lights, aurora australis. So they are made by processes in the space between the sun and the earth, kind of a really big domino system of a bunch of different things starting from the sun that eventually cascades into the Earth's upper atmosphere, and can also happen on other planets as well. In this field, it is connected to a lot of different areas of NASA. And so studying how those things connect, how the charged particle environment of the upper atmosphere connects to the Earth's weather systems, which are far, far below that. And the more familiar atmosphere, that's one of those connections. This system also connects out to further out in space, kind of more the realm of astrophysics. That is very interesting as well. But we kind of have our local natural particle accelerator that we live in and we can see the effects of. So that is really exciting. And there are also, so there's a lot of like this basic understanding and questions. And there's also a lot of applied questions as well, because the particles from the sun and how they impact the Earth's magnetic field region can have effects on our satellite systems, on our astronauts, on our technologies on Earth. So there's a lot of our field that is driven by understanding all of the system in order to protect those systems. So it is very, that's called the applied aspects of space weather, if you've heard of space weather. So this little kind of cartoon shows what happens as energy impacts the Earth's magnetic field, these kind of purple lines here, and actually gets stored on the night side of the Earth system, way out in space, away from the sun side. And then it gets released back to Earth and rains down on the upper atmosphere as the aurora. We will get more into that. This is a super large system. So the distance from the sun to the Earth is 93 million miles. And if the sun was like your wingspan, the Earth would be maybe just the size of your thumbnail or something like that. So we're out here a long way away, and the sun is giving us not just light that we are more familiar with, but also constantly bathing us in charged particles and a mixed environment of that. Sometimes really strong, huge amounts of charged particles come out. Sometimes they're more slow, and that's why we are constantly, the aurora is constantly changing, and we need to monitor the system as well to see what it's doing. And we only have a couple of satellites that are in between the sun and the Earth that can give us a handle on how to model this system. We can watch the sun and what happens, but we don't know all the parameters. And because we're so far away, there's also a lot of uncertainty that can creep in. And, like a normal weather forecast, that has some uncertainty. And this has a lot more uncertainty, which is why it's exciting, but also difficult to tell you how strong the aurora will be. Generally, at Aurorasaurus, we, you can get a heads up a couple days in advance, but to really know if the aurora is going to be dancing above the Hamptons, it's really only a couple hours of warning. And so I'll be talking a lot about a recent event that happened last year that was the largest event driven by a lot of activity on the sun. And it was the largest event in 21 years. So really exciting and beautiful. And it also had some important space weather impacts. In this case, some of the systems that were affected include GPS receivers that farmers use for planting and tractors and things like that. And those systems went offline, which had an actual significant financial impact as well. And I'm sure many of you know about some of the other impacts through time as well on different systems. So we have a couple different views of the sun here, of the disk of the sun during this really active time last May, and then of the wider environment, kind of the wide field view, where you can see the coronal mass ejections that came towards us and caused this activity. Let's see. Another sort of deeper dive here into space weather. This is a slide from NOAA and the Space Weather Prediction Center, which is in charge of the operational space weather forecasts for the nation and for all technical systems that could be affected by this system. And so you can see this slide from last May. They had a number of warnings for systems that could be impacted. And fortunately, a lot of these warnings got to the right people, and they're in industries, and there weren't a lot of negative effects. But certainly, there were effects on HF communications, ham radio operation, GPS, power grids, some spacecraft, all kinds of things. So that's just a snippet there. I'm going to go into a little more about auroras now and sort of the last step of all of the domino process here. which is often a very good question people ask, how the colors are formed. And so the aurora is happening when particles from space that have been come from what we call the solar wind and are captured in the Earth's magnetic field region um, are they get swirled all around, and that energy gets stored, and then it gets released. And these particles travel along the magnetic field lines, and they're mostly electrons that shoot into the upper atmosphere. And there they start to interact with some particles that are part of our atmosphere, but very, very high up. And it's in different, it's not like the air that we breathe. It's not dense and it's not mixed. But you do have those collisions that transfer energy and cause the particles of the upper atmosphere to light up. And the way that happens is when oxygen particles are impacted at high altitude, it glows red, and then the particles continue to deposit energy, and they bounce off some other atoms, and then there's more and more atoms, and around 100 kilometers or 60 miles, they really create a lot of green light that's also created by oxygen atoms, but at a different altitude. So you get a wide height range of green in the aurora as well. And you can even get, sometimes the particles are really energetic, and you can get these incoming particles kind of go through the oxygen layer, and they still have a little bit of energy, and they hit the next layer down, which is N2 molecules. And there you get a different kind of chemical transition, different wavelength of light comes out, and it's a very pink kind of cool color. So if you've seen all those colors, they also mix the way that light does, and you can get some even more rare colors through that as well. Another view of this is shown here with sort of the height being shown, the range of oxygen, and then the molecular nitrogen. There's also some ionized nitrogen above that, a little bit of blue. You don't often see that much. And then a lot of red can be at the highest altitudes, but it's often pretty dim until you might get the largest storms, in which case you actually have more particles that can cause a lot of red. And what did we see in May? We actually saw a lot of red and pink and very unusual colors. This is kind of just a compilation across the US. The aurora was seen all over the world. It was even captured by cameras, really sensitive cameras, but cameras in very unusual places. The country of Oman, they had some observations of aurora very far south compared to where it's normally seen. But you can see such an unusual storm. You can see kind of maybe more green at the more northern states, and then a lot more red as you go further south. And that's because the red is happening at really, really high altitude, and thus it is visible from an angle very far south. And so we'll delve more into where people saw it and how they saw it and how you can see it as well. This was the biggest storm of 20 years. Aurorasaurus has been around for more than 10 years. This is the biggest storm we've ever seen. And it was the biggest storm ever captured on digital cameras and cell phones. And we now have the technology that makes capturing these incredible images, cameras can see the aurora better than our eyes can. So cell phones can pick up really good photos of aurora now. And then, of course, there's also really talented photographers who are using digital cameras, SLR cameras, and uh, capturing even more. A couple of those are highlighted here on this slide. And those are some of the volunteers with our project. And these images have also been published by NASA. And the one in the upper right is in the current NASA calendar, which is a really nice publication and really great to see. So auroras can tell us about space weather. They can also tell us that our planet has an atmosphere and a magnetic field, which is critical to why we can live here. So they may be very important for um, for life on other planets as well. And there's a question here about, question about colors. There's a lot of differences in colors. So you can, with our project, we are collecting images further south than there are a lot of cameras. And so during these largest storms, we haven't ever really fully imaged something like this, which is called a superstorm. And so we don't know all of the ways that this system creates the reddest auroras at the furthest south for us in the Northern Hemisphere, at the furthest southern most locations. So this is a research question, actually. This is why it's important to, why we're collecting observations, and we're also trying to do some work towards intercalibrating, the vast array of cameras and phones and things out there. We have a really nice blog post about different kinds of red aurora and what that could be due to. So if you're especially curious about the red that was seen recently, that would be a great place to look. Okay, I'm going to take a sip of water. And segue just a little bit into a recent event called the Heliophysics Big Year that I mentioned earlier. And that is an actual NASA event that just wrapped up at the end of December. But we had so much going on last year that that we wanted to celebrate it, and we wanted people to get involved. So of course, we had multiple eclipses, and the Helio Big Year actually began in October of 2023 with the annular eclipse that went across the US, and then the April eclipse that went from Texas to Maine. I hope you all got to see that as well. And then we've been celebrating the fact that people can take part in helping the science, and there are real science questions along with the eclipses and along with our missions as well. So there's two other important elements of the big year. One is the closest approach to the sun of the Parker Solar Probe. So it got within 4 solar radii of the sun. This satellite that is one of our flagship missions to understand how these particles are accelerated and suddenly burst forth from the sun. We need to send a probe closer to actually measure those particles. And so that's a real engineering marvel, and something we wanted to celebrate at the end of the year. And then something that also is happening is that the sun is at its maximum of activity. So that's why there was so much aurora last year. This is going to continue on into this year. There is going to be a lot of aurora large storms this year as well. And this is also why the last storm of this magnitude was 21 years ago. So this solar cycle is 11 years. And the last solar maximum was about 11 years ago. But that one thing we don't know about the sun is each maximum is not the same. So the last maximum we just had was a little bit wimpy, and there weren't huge storms like this one. So that's why you actually have to go back two solar maximums to the last storm of this size. So this is another cartoon about the Parker Solar Probe, and I'm probably gonna skip it a little bit. Laura's been putting some great links in the chat. There was a lot of coverage of this from NASA and our great communications folks at the end of December. Actually, it was December 24th. So people might have missed it. And those are, you can catch up. That's available now too. And of course, the data was just collected then. So the actual study and understanding of what was collected is going on now. Let's see. So just to briefly mention a few of the other aspects, studying that relate to citizen science. So both of these, the eclipses and the solar max, have a lot of good opportunities for citizen science. Eclipses are one of the only ways in which we can actually see the solar material, the solar wind that is very close, like just as it exits the sun. We can't see that normally because the sun is too bright, and the instruments that we have that block out cause like an artificial eclipse. They have to block out more than just the disk of the sun. So you can see in this image here how much we miss, and you can see kind of the size of that ejection, and how there's this region that we can't actually measure. But when eclipses happen, the moon is just perfectly sized to completely block the sun, and we can actually study the outer corona of the sun. And there's a lot of questions about how hot the corona is. We don't know why it's so hot, and we also don't know why and where exactly activity will happen. And so the way that citizen science was used with the eclipse is that there were multiple teams of people all along the path that, you know, each location on Earth, you would only see this stunning sight of the corona for a couple of minutes. But if you put people all along the path, you have this force multiplier to take all of these observations. And so there were many different projects where people were contributing observations of the corona and other related aspects. Some of them were using normal cameras. Some of them were using their cell phones. Some of them were using different types of telescopes and teams of people fielding those instruments. So we can observe the corona from space, but we don't know how hot it is, and we can't get really that close. So there are a lot of open questions that, again, people, some of the volunteers, some of the scientists who stood up those projects are working on right now. And this is one of the open questions in auroral physics that Laura mentioned at the beginning. This is actually an image of Steve. I will talk more about Steve, but you can admire this unusual aurora here. The normal aurora is down to the north in the lower part of this image. I hope you can actually see my cursor. I think you can. So another thing about citizen science is that it enables people to be asking their questions in a more systematic way so that we can ask and answer these really large questions, and members of the public can be contributing to collecting that data, interpreting results, and asking the questions themselves, like, what is this about Steve? Or about other things. And this works on a really large scale. And there's a number of cool books about the discoveries in many different fields. So it's been really an interesting journey to take part in because it's so multidisciplinary as well. NASA is quite into citizen science. There are a number of NASA projects. NASA collects a lot of data with its satellites, and so there's a bunch of projects where you can help analyze the data. And there's also some projects where people can go outside or help collect data themselves. So science.nasa.gov/citizen science is the place to go for that. There's also another clearinghouse for citizen science projects that you might like to check out. It's called SciStarter, and they host an event, April being Citizen Science Month, and they have a really good search capability. So if you're looking for a project on butterflies that you can do with your 6-year-old grandchild, their search can help you find that project. Let's see. So a couple more pictures of the eclipse here and the different observations. As I mentioned, since people were all along the path and studying this constantly changing corona, that enables us to check our models for the first time in real time, or not exactly in real time, but some really advanced models of what the corona should look like to actually check them against data. And some of the beautiful features, these chromospheric features on the sun. I saw some of those for the first time. Those were really, really neat to see. And the aurora is, to me, it's definitely as beautiful as the eclipse. And maybe more mysterious or it's harder to track because you don't know when it's going to happen still. But eclipses are really big, great events for getting people together. There's a few other projects that you can do anywhere, anytime that I wanted to mention. Some of the amateur astronomers in your group might be interested in this project, Exoplanet Watch. And you can help find transiting exoplanets using your own telescope or other remote telescopes. There's also projects to track phenomena called sprites that happen above thunderstorms. And that's a really cool project. And then there's a project coming out soon with another satellite that's launching this year called EZ. And that project actually measures changes in the Earth's magnetic field due to space weather. And it's a really easy to build Raspberry Pi small cheap computer and a magnetometer on one of these chips. And this is actually a project mostly for high schoolers or college students and teams there. And one final celebration of the heliophysics big year that I wanted to mention is a collaboration that Aurorasaurus recently led in collaboration with the Astronomical Society of the Pacific. And they had a project called Eclipse Ambassadors, where they paired amateur astronomers and undergraduates to do eclipse events all across the country last year. And some of those undergrads got to come on a heliophysics winter field school and experience the auroras as well, and experience citizen science and learn more about the field from that aspect also. So this is unusual. Well, it was the first time that we did this. It was a big success, and we hope to do that again. It also feeds into the citizen science that our folks do regularly, that the volunteers do. because we can, like the students had specific tasks, experiments they were trying to do that helps us analyze the wider amount of citizen science data. For instance, they can all use their phones to take different pictures of the same aurora, and then we can better distinguish between what different phones are doing. So that's one little example. Yes. So what makes a good aurora photo for Aurorasaurus? So basically all photos are great. They are best if they're raw and unedited. Um, we want to know exactly where you were and what time it was. That's critical information. You don't even need a photo, actually. That's the minimum amount of information you can contribute. This photo right here is an extraordinary citizen science image because it has a vast amount of different phenomena in it, including Comet Neowise, and I think this is the ISS, and some unusual auroral features here on the sort of southern western side as well. Excuse me. This photo was taken by one of our ambassador volunteers, the extraordinary Donna Locke of Manitoba. So they have it a little easier down there to see aurora, up there to see aurora, but people are noticing things. Donna is noticing things and always wants to learn more. Sorry. So this is another incredible image from one of the aurora chasers here in Washington State, not that far from me. I did not capture any of these, hardly any of these images of aurora in 2023, but Prisco Blanco, who lives not too far from Walla Walla, did, and really there's an extraordinary variety of the aurora that can be seen. And it does take time and knowing when to go out. And a lot of he has a lot of good photography skills and spots to apply to that. The different types of aurora that we see, our project, our project has when you go to submit a report, it asks you a few simple questions. And one of the questions it asks you is if you know the type of the aurora that you see. And there are many different types of aurora. Hardly any of them are very well defined. But we break it down into three main types of aurora that we ask you about because it is actually significant where you were and whether you saw one of these types. And those three types are, the first is called discrete arcs, which are mainly like the usual kind of curtain aurora that you saw, that you could see. And it could be one, it could be multiple, they could be over the sky. We also ask you questions about how fast they're moving and how much of the sky they cover. And then the other main type that you might see is it was just a like diffuse glow. And especially for some of these red events, all you might see would be just red in the sky. And so that would be the type to choose there. If you're out after midnight, you might be able to see really, usually dim, but spooky, pulsating patches that turn on and off. Those you have to let your eyes adjust and have kind of a dark sky location. But that is a really different type of aurora that involves different types of waves in the space environment. And so it actually happens after midnight for a specific reason, because the particles are flying through these waves that happen to live in a different region of space that we would see more after midnight. And then there's Steve. Steve is not one of the main types, but you can always enter some more information in the notes field, like if you know that you're seeing Steve. As I mentioned, there are different types. Sorry, there's a difference between what our eyes can see and different people's eyes and what cameras can see as well. And it's just that cameras are actually more sensitive to color than our eyes are at night. The way that we see color works during the day much better than it does at night. So there are many different ways that you could see aurora. You want to find a safe, dark place with a clear view towards the north, preferably not too much light pollution. You can be signed up for our alerts and also other space weather forecasts that there might be activity. You actually want to be checking the weather forecast, the regular weather forecast as well, of course. You might have some webcams that could help you out. For you guys in the Hamptons, there are some webcams on in Maine that are good and would tell you if they're seeing aurora in Maine and how high in the sky it is. Yeah, there might also be other aurora chaser groups, regional groups, like on social media. I don't know what groups. I don't know too well what groups there are in the Northeast. I think there's one on Facebook called Northeast Aurora Education, something like that. I think I'm in that group. But there might be some more for New York State as well. And the aurora is quite fickle, so you definitely have to keep trying, and it might take a few tries. I'm not sure how, if there's, I know in the West, we're generally blessed with quite a bit darker skies. I have a mention here of the Central Idaho Dark Sky Reserve, which is a great place to go if you want to see really dark skies in the US. It's, where's my cursor? It's kind of here in Central Idaho. And they have a cool project also funded by NASA, where the students are helping to measure and the light pollution that they have and keep that in really pristine dark skies. But you always want to do, as best you can for where you are. We also have a blog, and we have a lot of kind of go into more about the auroras and different aspects of research around the auroras on our blog. So we have a lot of stuff there, as well as on the Learn tab of our website. One of our recent blog posts that was pretty popular was this Aurora Altitudes hat, where it is actually knit and it is actually scientifically accurate in terms of the altitude and how each row, I believe, is 6 miles in altitude. And so you can see, way down here is where the highest clouds are in row 2. And then the aurora is happening way up here around row 10. And the red aurora goes even higher up. So credit to Laura for coming up with this, and credit to anyone who wants to follow the knitting pattern and make their own aurora hat. We also have a number of educational resources and collaborations. We have a virtual aurora chase. We have collaborations with university students and graduate students. And then we actually have a card game for kids or adults about the different factors that you need to consider to be successful in seeing the aurora. And it's always a game of chance. So Sometimes your cards are favorable, like you have a public access park. And sometimes they're not favorable, like, oh, there's bears around. And so in the end, you'll roll the dice, and based on how favorable your conditions were, it'll tell you whether you saw aurora or not. So that's a good way to practice. And then we have some other teacher resources. If there are any teachers out there, we're always happy to talk to teachers and students. And lastly, almost lastly, I will talk a little bit about Steve. Actually, I'll play the video about Steve.
People were out observing the aurora, and they started noticing something that was overhead as well when they were seeing the aurora far to the northern regions. It was unlike most aurora. Talked to the scientists, we didn't know what it was, and together they said, we'll keep taking observations and we'll call it Steve in the meantime. Steve is mostly a very narrow purple arc, and sometimes it has these little green features that go along with it as well that are kind of like waving fingers or a picket fence. That means that there's plasma physics happening up there to cause that light and to make these little discrete features that we don't understand yet. We now have some satellite observations from the ESA satellite called SWARM that show that Steve optically is associated with a very strong flow in the particles in the ionosphere, the upper level of our atmosphere. Steve is important for a number of reasons. It's really exciting that people armed with cameras all over the globe can capture something that we didn't fully understand and shed new light on that. It's also really exciting that this happens further to the south where there are more people, so it might be a kind of aurora that more people can see than the usual kind. We're now able to look up at the sky and see things about the aurora and this sub-auroral region that we never understood before, and then we can correlate that with our traditional observations and lead to greater understanding.
All right, thank you. Thanking myself, I guess, giving me a chance to drink some more tea here. So this is a compilation actually from the Alberta Aurora Chasers, which is a great group in Canada that we worked with on the discovery of what Steve actually is, and the fact that Steve is something that had been seen by satellite instruments, but we never actually knew was visible. And again, here it's much brighter in the camera than to your eye. It's mostly very gray and very rarely this bright in color. But it's an unusual, intriguing, different kind of aurora. Oh, I don't have the other slide I thought I had in here. But most aurora is caused by particles that kind of go plinko down into the atmosphere and deposit energy. And Steve is actually a jet that goes east to west and glows. And we don't fully understand how it happens. And it's always further south than the usual aurora. And it's almost always a very narrow east to west kind of boundary that happens maybe 10 or 11 o'clock at night, before local midnight. And so it's being researched. A lot of aspects are being researched in the last 5 years, and there's still some mysteries. But one thing that we do know is that it is not entirely new. And it was actually looked at and characterized by a Norwegian scientist over 100 years ago. And they took some black and white photographs of Steve, and that scientist, Carl Stormer, called them feeble homogeneous arcs of great altitude. And for various reasons, a lot of his work in the early 20th century, most of the field of heliophysics really exploded after the space age. And so this unusual, lower than usual latitude aurora didn't get the study that until recently that we understood what it is, and we're looking into it more. Just to provide you a little bit more specifics here as I wrap up about Aurorasaurus, you can register for a free account on our website, aurorasaurus.org, and you will receive our newsletter and email notifications when the aurora can possibly be observed near your location. There's actually two levels of alerts. One of them is when the model makes that prediction. The model is very coarse. The model could be correct, could be not correct. And the second one is when people around you, actual citizen scientists around you, are reporting aurora. We have a stronger alert that can go out for that. But we need your reports to generate that and help others. And then, yeah, you can also submit your sightings anytime. The location and the time an agreement to our terms of use for researching your contribution is what's required. The locations, there's privacy controls and settings for the location to be safe, to be shared as well. And then you can check out the map on the website and you'll see where the aurora is predicted. Right now, you will see also there's a lot of talk about what's happening in the solar wind and the data that we can monitor in real time. If you click the plot icon on the front page, you'll get one plot that takes those multiple parameters into account and goes up when activity is happening, increasing, and should be a little bit easier to read than some of the other. You'll hear people talking about you have to worry about the velocity of the solar wind and the magnetic field strength, and this calculation takes those both into account. So it's handy in that sense. What else? Yes, during May, people all the way down to Texas and Alabama received our reports. And a special invitation here, we are having an event where you can report any aurora that you've seen or talk to us about special topics that you might be interested in, special questions you have. The event is happening next Saturday, March 1st. So even though this talk has been a long time coming, it is well timed in that sense that we would love to have you join us. It's a little bit late East Coast time, but we do this twice a year and we try and get the time zone so that people in the Southern Hemisphere can also join us. So that's the timing there. And I will happily take a few questions. Thank you so much. I know I've gone quite long. I've been talking for quite a long time. So thank you.
Sure. There's a great question. The most common question I've had tonight is, can they get a copy of your slides?
Yeah, we can make that available. We can work with Donna to get that on the website, I think.
Fabulous. We have the question, do binoculars offer similar or better colors like a camera than the eye when you're watching aurora?
I am not familiar with binoculars that could enhance your night vision or your colors specifically. That'd be a good thing to try to see if it helps you. I don't think it will. If you had something fancy like night vision goggles, that makes it magnifies the photons like a lot. So you could actually see a lot more of these particles and the arcs and everything. It wouldn't help with the colors specifically, though, because the night vision goggles aren't color sensitive like that.
All right, I have the
It's a good question.
Yeah, it's a great question. I have a question from Josh. Do SAR arcs only form during or after a massive solar storm, or can they form when there's a weak solar storm too?
I think they can form when there's weak solar storms as well. A lot of the questions about SAR arcs, which stands for stable auroral red, is previously, like decades ago, they were thought to be kind of stable and pure red and associated with these large storms. But we now have more sensitive technology, so we are now finding that they vary in brightness during storms. They may happen more with not more with weaker storms, but they may also happen with weaker storms, and they may even have some other a little bit of green along with beside them too. So hard to
Fabulous.
answer. Yeah.
Yeah, thank you. I have a couple of people asked about auroral sound. Can you say something about that? Does the aurora make a sound?
Yeah, I saw one of those questions, and it sounded interesting. And it is so we do a lot of work with people who are enthusiasts and or have a question like, I think I've heard something, or I think I've seen something. What do you think I should do? And so I did not mention, but I was trying to, that we have a network of ambassadors and volunteers around the world who are often leaders of their local groups who have a lot of expertise. And so those folks, good to bounce ideas off of. And we also have a lot of those sorts of volunteers at our report-a-thon. So again, another good place to talk to people who may actually have their own observations of sound, possibly. We have, so we definitely have interest in that. We have a recent blog post on that. And it's the sort of thing that is extremely hard to, I guess I'll say in general, has been extremely hard for scientists to verify. But anecdotally, people all around the world have reported hearing sound, especially in very quiet locations. So it's another question that's very well suited to citizen science. And so we're
Yeah,
all about it.
absolutely. And I actually posted a blog post that we did recently with one of our ambassadors who's a historian of Aurora, looking at the history of that question, and how
Mm-hmm.
that was investigated during the first and second polar years. Um, just moving through, what is the difference between air glow and aurora?
Ooh, that's a good question. I So air glow, Steve is a little bit more like air glow because it's more of an interaction between sunlight or heated particles as opposed to particles raining down and causing light. But I'm probably not going to get this entirely correct. But I think most air glow is caused by the interaction of uh, um, sunlight and particles in the upper atmosphere. So it's a more it does vary throughout the year, but it's mm, not as much the larger system of sun and how they interact with the earth. And it's not a great explanation. Sorry about that. I'll
Right.
come back to that one.
We have a quick question from Josh. Um, it's a question about some of the scales that are used to measure aurora. A lot of times when we see aurora reports on the news, we'll see them measured in KP 1 through however, so 1 through 9 and a G scale. He's wondering the October 10th aurora event was classified as a G4, but wouldn't it have been a G5 for part of it?
Um, I think if it was a G5, if it hit G5, that would have met that they would have said that. I'd have to know more about the question, but as far as I'm aware, there's a specific way that I think that the G scale pretty much goes by what the maximum recorded um, uh, disturbances were. And those are officially determined by NOAA. So that would be the place to look for more information on that. There's also, I can say that there's quite a bit of variation in, I don't know if it's variation so much, but the KP scale, especially, historically is a parameter measured by the magnitude of small variations in magnetic field measured on the ground, actually. And so historically, that's a 3-hour index that you calculate, and then it wasn't a real time or a forecast index. It actually pertained to the last 3 hours of what the activity was. And so nowadays, there's a lot of apps and proxies for KP, and they are not highly recommended because they're often based on until you measure the solar wind, you can't really predict more than an hour or two into the future accurately at all. So for our purposes as aurora chasers.
That's a great thought. Thank you so much, Liz. We have a question from Donna Locke. Did the group that went to Alaska decide which cell phone took the best aurora photos or videos?
I there was one time, I don't think there's an absolute answer to that, but I do remember at some point somebody was like, "Oh wow, your Motorola is really good." And it was something unusual. I can't remember for sure if it was a Motorola or not, but I think that what it was is it probably had a little bit more of a green sensitivity, and a lot of the cell phones have kind of a lot more red sensitivity. So those are things that we need to more try to get a handle on more quantitatively. And we didn't actually see, so we tried to do that experiment in, the students tried to do that experiment in Fairbanks. But unfortunately, the aurora that we saw was not super strong. So we didn't get a whole lot of color and brightness variations. And we only got a couple opportunities to do a little bit of that. So the jury is still out.
All right, thank you. Yeah, the sensitivity of camera lenses or camera sensors to different colors was something that had never occurred to me until I joined here. Um, we have a question about, we'll take two more questions, because I know we're keeping you all over, and thank you so much for sticking with us here. How were the May and October storms different?
Yeah, that's a really good question. And that is something that people are still studying. And that's also a reason that we're still looking for more observations. So the drivers were quite different. There were some unusual aspects of both storms. Um, I'm trying to another way that they were different to aurora chasers. May 10th was the stronger storm. It also there wasn't a lot of moon. The moon was really bright in October, or nearly full. So I might have to get back to you a little bit more on that also.
Thank you. And we'll go on and wrap this up with the conclusion of the heliophysics big year. We had a question about Parker Solar Probe's closest approach to the sun. How far away was it? Was it between Mercury and the sun, Venus and the sun? And how did it survive the heat and radiation?
Yeah, those are great questions. And the best place for that information is some of the links on the Parker Solar Probe interviews and things like that. So I don't work directly on that. So I believe that the closest approach itself was within like 4 solar radii of the sun. And so I think that's well within the orbit of Mercury. But I don't have the exact number off the top of my head. And then the other question about the engineering, I know there's some really cool heat shields, and then the instruments stick out. And that's one of the reasons why we have NASA has a lot of all of these instruments and satellites. Like you can't go up and fix them afterwards. You can't improve your heat shield. Once it's launched, it's launched. And so there was a gradual approach here to getting to the closest approach. There were a number of orbits in which the Parker Solar Probe was getting closer and closer, and it was carefully designed to monitor, not to just go all the way in and something bad could happen or something like that, but to have a graded and a very safe approach. And fortunately, they're usually conservative on those sorts of things. And so it survived very well, I think, and is still orbiting, is still making very close approaches nowadays too.
Well, thank you
Thank
so
you.
much, Dr. Liz. We really appreciate it. I just want to shout out one more time to our wonderful volunteer, Tanya, who has been moderating the YouTube chat for us today. Really, really appreciate everyone being here. And thank you so much to Donna from Hamptons Observatory for having us. Did you want to say anything else, Liz?
I will also say thanks, and thanks for asking those great questions. I will be thinking more about some of them. Stay tuned for the next talk, or you can come in March, March 1st, and maybe we'll have some updates on some of those things. But great questions, and thank you all so much for being here. Really appreciate it, and have a great night.
Thank you all so much. Have a wonderful night.